Let's take a look at an example where we have a motorcycle accelerating at 2.5 meters per second squared, east 40 degrees south for 4.0 seconds. It reaches a final velocity of 14.0 meters per second, south 70 degrees east. We're going to look to determine the initial velocity of this motorcycle. So there's a lot going on here. Let's write down what we know. We know that V2 is 14.0 meters per second, and we know the direction is south 70 degrees east. We also know the acceleration, 2.5 meters per second squared. The direction here is east, 40 degrees south. And we know the change in time, which is 4.0 seconds. The thing we're looking for here is V1, which is going to be a vector. And we can make use of the following equation, which we're going to have to rearrange. So the equation that we know is V2 equal to V1 plus AT. With a little bit of algebra, we end up with V1 equals V2 minus AT, and A is a vector there. If we take our new equation, it's going to give us a lot of information, and it's going to allow us to figure out what kind of drawing we're going to be looking for. So we should hopefully realize that this AT right here is actually equal to your change in velocity, right? And our change in velocity is v2 minus v1. So this is no different than just saying delta v equals v2 minus v1, which is going to help us decide what our triangle is going to look like. Okay, so let's start solving some of this, and we're going to solve as much as we can without having to actually do the subtraction here, because we're not going to be able to do that, you'll see, due to the directional challenges we're going to be facing. So we're left with 14 meters per second. The direction here is south 70 degrees east minus your acceleration, 2.5 meters per second squared, east 40 degrees south, times our time, 4.0 seconds. Now you might look at that and kind of say, okay, I can't really do much here. How am I going to be able to draw a picture? But if you realize that these seconds are going to cancel, well, now you're left with meters per second. Because again, that last term is actually just your change in velocity. So it makes sense that it should be in meters per second. So we're left with 14.0 meters per second, south 70 degrees east, minus 10 meters per second, east 40 degrees south. It's always preferable to add vectors instead of subtracting them. So that leaves us with 14 meters per second, south 70 degrees east, plus 10 meters per second. And since I've changed the sign, I'm going to have to change the direction. That's west 40 degrees north. Because of this, we can now draw a diagram and add our vectors head to tail. We're going to start off by drawing a little bit of a coordinate plane. And this is just to help us out so that we can see where exactly it is that our vectors are going to go. This is quite a difficult question. So I'm going to draw out my coordinate plane. Okay, and I'm going to draw several of these. So the first one I'm going to look at is my 14 degrees south, 70 degrees east. So that's going to come up maybe something like this, 14 meters per second. Next up, I have my next vector, which is this one here. It's going to come out at an angle of 40. So maybe something like this, right? And this is 10 meters per second. And the last one I'm dealing with is whatever this guy, the resultant is going to be. And that's V1. It's not quite parallel to the horizontal, but it is pretty close. So if I go ahead and label some stuff here, this angle is 70, which means that this angle here has to be 20, which gives us an angle, this one we said is 40, Remember, this goes to the horizontal, but it also tells us that this angle inside here is 20, as well as this angle inside our triangle is also 20. The one at the bottom we got from a Z pattern with the one up there. So now we have enough information to use our cosine law. So V1 is going to be equal to, I'm going to take the square root of this entire thing, 14 squared plus 10 squared minus 2, 14, 10 cos 20. When you solve that, you're going to end up with 5.73 meters per second. So that's just the value of V1, and it has nothing to do yet with the direction, right? So we've just found this value, the length of that green line. I can now use the sine law to tell me what my angle is. So I have sine theta over the opposite side, which is 10, equal to sine 20 divided by the opposite side, which is 5.73. That allows me to rewrite my equation like this. Which gives me an angle of theta of 36.6. Now, that doesn't quite match up with my drawing, so obviously my drawing is not quite to scale, but that's okay. We do the best we can with our drawings to ensure that our answers are as close as possible. So if that is 36.6, that tells me that the entire angle in terms of relative from east to north is going to be 70 plus my angle theta that I just solved for minus 90. And that's going to give me my angle relative east to north, so 16.6, which tells me that my final answer here is 5.7 meters per second, and we'll respect significant figures, east 17 degrees north, by using the sine law. So again, remember that we've solved for V1, and V1 is now equal to 5.73 meters per second. We can make use of our sine law, which tells us that sine theta over 10, because we're going to be looking for the angle inside here, which is not necessarily right beside the horizontal, but it's going to be close. Sine theta over 10 is equal to sine 20 over 5.73. We are allowed to rearrange this such that theta is equal to sine negative 1, 10 sine 20 over 5.73, which gives us an angle of 36.6 degrees. That's the entirety of the angle, but that's not exactly what I'm looking for. I'm looking for just the angle on the inside.